In this video, we're going to be talking about partial fraction decomposition, what I'll abbreviate as PFD. Now, with partial fractions, this is going to be a technique to help us to integrate what we call rational functions. So keep in mind, rational functions are just functions where the numerator and denominator are polynomials. So you might have something, let's say p of x over q of x, where both of these are going to be polynomials, okay? So if we have these rational functions, our goal is to turn this single rational function into multiple other rational functions, each of which are going to be easier for us to integrate. So for example, this p of x might split up with some fraction here, and then another fraction here, and another fraction here, where all of these denominators, so this, and this, are going to be factors of q of x, okay? Now, the reason we might do this is because the integral of this original rational function might be rather complex. Maybe we don't have a way to do it. We tried u sub, whatever we've seen in the past, those techniques we know don't work. But if we were to look at each of these individual rational functions, we might be able to integrate each of these independently. Okay, so that's our goal. We're going to take some ugly single rational function and we're going to try and decompose it or break it down into a combination of those rational functions, each of which we should know how to integrate. So with that being said, let's look at two different integrals here. Let's say I give you the integral of 4x plus 1 over x squared plus x. And then I give you another integral, which is 1 over x plus 3 over x plus 1. Looking at each of these integrals, which would you say you know how to integrate? Hopefully, we can all agree that the first integral, I don't currently know how to integrate it. It almost looked like it could have been a u sub, right? If we let u be x squared plus x, but the derivative is 2x plus 1. We've got an extra 2x hanging out up here, right? So this is going to be kind of a problem for us. Whereas over here, each of these integrals fits a natural log rule. So harder to do, easier to do, right? This was a single rational function, just like what we presented above. And here on the right, we have a combination of rational functions, each of which we know how to integrate. Now, what if I told you that these two integrals were equivalent? How could we prove that? This is the whole point of partial fraction decomposition. So what we're going to go ahead and do is we're going to start by just adding 1 over x and 3 over x plus 1. Now, our goal is to make sure that this addition ends up being equivalent to this. So how do we go ahead and add these two fractions? Well, we need to get a common denominator, right? When you add fractions, you need to have a common denominator. So what we're going to do is we're going to take 1 over x, and we're going to force a common denominator by multiplying the numerator and denominator by x plus 1. Similarly, we'll do this with the 3 over x plus 1 here. We're going to get a common denominator by multiplying the numerator and denominator by x. Okay? Remember, the common denominator in this case is x times x plus 1. It's the combination of these two denominators multiplied. Now, we go ahead and make our common denominator x times x plus 1. The numerator of this first fraction here is x plus 1 times 1, which is just x plus 1. And then over here, 3 times x would just give me 3x. So all in all, x and 3x would give me 4x plus 1 over, if you were to multiply this, we could see x squared plus x, or we can leave it in its factored form. And there you have it, right? We just proved that this term is equivalent to this term, and therefore the integral of this is equivalent to the integral of this. Now, obviously, we're not trying to go from this form to this form, right? We're trying to go the other way. We're trying to somehow take an ugly mess and turn it into a simpler form. So how are we going to do that? Well, let's look back at the process we just did, right? So if we can go this way with it, we should certainly be able to go the other way. So what we're going to do is we're going to start with this term. And it might be even better to start with the factored version in the denominator. So when we go ahead and approach these problems, what you're going to want to do is, especially right when we're doing partial fractions, you're going to want to factor your denominator always. Okay? So you're going to factor this. Here we get x times x plus 1. Now what we're going to go ahead and do is we're going to split up the rational function into two rational functions where each rational function that we're going to create is going to have this denominator or that denominator. It's going to basically split the denominator's fractions up. So one rational function here is going to have the denominator x. The other is going to have that denominator x plus 1, that factor there. And then what we're going to do is we're going to have to try and figure out what in the world are these numerators supposed to be, right? Of course, I should know that they're going to be 1 and 3, right? But I need to prove that. I need to go ahead and solve that those are indeed 1 and 3. So how are we going to do this? Well, what we're going to do is we're going to go ahead and assign these numerators arbitrary value. So we're going to call this a and b. We're going to give it some constant. And our goal is to find a and b, okay? So all we did so far, split up our denominator into its factors, and then we created separate rational functions, each with those denominators, putting a constant up top for us to be able to solve. Now, just as we did in this process up above, we want to combine these so that they are going to be one single term. Right? So the goal here, again, to solve a and b, is if I were to combine these to get a common denominator, which would be this, I could then compare the numerators across the board, right? So if you have the same denominator, you can ignore the denominators and just compare the numerators. So here's what I'm going to do. I'm going to take a over x. I'm going to multiply by x plus 1 over x plus 1 to get a common denominator. So what I'm going to do here is I'm going to go like this. So I'm going to take a, no, I'll just do it over here. So I'll take a times x plus 1, and that's x plus 1. There's my common denominator. Then I'm going to take b over x plus 1, and I'm going to multiply it by x over x. Okay. Now, this creates the common denominator, x times x plus 1. And my numerator is a times x plus 1 plus b times x. Okay. Now remember, this is all equal to 4x plus 1 over x times x plus 1. And so if this is equal to this, I can ignore the denominators, and therefore 4x plus 1 should equal a times x plus 1 plus bx. So I'm going to go ahead and write that over here. This tells me that 4x plus 1 is then equal to a times x plus 1 plus b times x. Okay, so this is the equation that's important to me. I need to now go ahead and solve for a and b using this equation. So how am I going to do that? Well, we have two different ways that we're going to approach this. So one way is a way that we refer to as, or at least I refer to as, a polynomial mirroring method. And then we have another method that we're going to use, which is called the Heaviside cover-up method. Okay, so these are two methods, and I can put method over here. These are two methods that we're going to use in order to be able to find these coefficients, right, or a or b and so on. Now, deciding which one to use is going to be the main part of this technique. So you'll have to figure out which one to use in which scenario. Generally, we typically use the Heaviside cover-up method for most times, just because this actually solves a little bit quicker. But we'll see that there are opportunities where this first method is going to be beneficial. Okay, so we're going to walk through each of these, show how we can find our a and b using both of these methods, and then kind of talk about what we're noticing, what patterns we're seeing here. Okay, so let's start off with doing our first method. So the first method, we're trying to mirror both sides. We're trying to mirror our polynomial. So right now, this is a polynomial. We're trying to mirror this polynomial to that. What that means is I'm going to write this expression here, 4x plus 1. I'm going to put that to be equal to our right-hand side here. All I'm going to do, though, is I'm going to multiply out. So I'm going to distribute everything. So I'm going to get ax plus a, just distributing the a to both of these terms. And then I'm going to add bx Combining the terms that have x in it, you get a plus b times x. Okay, this is just taking these two, factoring out an x, right? Pulling out an x, and you're left with a plus b. And then you have this a remaining. So we're just trying to make it look like a polynomial, right? Something with x, and then a constant, something with x, and then a constant. Once we're at this step, now we mirror. That means 4x is supposed to be equivalent to a plus b times x, because these are the only terms with x in it, right? So if these are the only terms with x, they have to be equal to each other, or else the polynomials on the left and right side are not going to be equal, right? So that means 4 is supposed to be a plus b. You just drop the x's. And for the constants, we know that 1 is going to equal a. Cool. Easy enough, right? So 1 is equal to a, or a is equal to 1. I have one of my constants. I can just throw that over here, plug in a is 1. You get 4 equals 1 plus b. I find that b is equal to 3. Awesome. So I have a is 1, b is 3. If I brought that back up to my expression that I decompose this in, that shows me that 4x plus 1 over x squared plus x is just equivalent to a, which is going to be 1 over x, and then b, which is going to be 3 over x plus 1. That is exactly what we anticipated, right? That was what we were hoping for way back up above here. So that is one way for us to solve our coefficients, right? We kind of mirror both sides, we make them look alike. Now, the Heaviside cover method is going to be a method where we strategically choose x values to cancel out our terms. So again, I'm going to rewrite our working equation here. So this was 4x plus 1 equals a, x plus 1 plus bx. And what we're going to do is we're going to strategically choose x values so that terms cancel out, right? So that we can cancel out one of the two coefficients, whatever we're solving for, a or b, and then get one of them by itself. So in this scenario, I would choose, for example, x to equal negative 1. And the reason I'm going to do that is because when I choose x to be negative 1, this right here would cancel out. I would get negative 1 plus 1 would be 0 times a. So the term with a in it would disappear, and then you would just be left with an expression only in terms of b for which you could solve, right? So if I plug that in, plug in x to be negative 1 everywhere, you get negative 4 plus 1, so that's negative 3. Like I said, on the right side here, this cancels out. Negative 1 plus 1 is 0. You multiply a by 0, and then you get b times negative 1, which is negative b. That gives you b is 3. Well, look at that. Just as I anticipated, right? And I did not write 3 over here for some reason. Okay, so b is not equal to some c-looking thing. B is equal to 3. Okay. So we got that, right? Plugged in negative 1. Now, what would we choose for the second value? What strategic x value could you choose to cancel out now the b coefficient to get just a by itself? Well, choose x to be 0, right? 0 times b would be 0. So at x equals 0, you get 0 plus 1, 1 equals a times 0 plus 1, which is a times 1, or just a. And look at that. 1 equals a, or similarly, a equals 1. Great. Again, the solution we wanted, okay? So both of these methods we're going to use. Sometimes we want to use them in combination. So you might need to, for example, use the cover-up method when you're doing some linear terms just like this. But it might prove to be a bit more useful to use this mirroring method when we have some quadratic terms in our expression, okay? So bringing us back to our flow, remember our goal was we were trying to integrate 4x plus 1 over x squared plus x. And what we showed was that this was equivalent to, after the decomposition, a over x, which a we have turned into a 1 over x, and then a b over x plus 1, which we showed b was equal to 3. And then we would be able to go ahead and integrate each of these. At the end of this, this should become ln absolute value of x for this first term. Our second term would be 3 ln absolute value x plus 1. And then we'd throw a plus c on there because we are working with an indefinite integral. So this would be our process. We take this first rational function, we break it down using our partial fraction decomposition process, right, which requires us to use one of these two methods here to solve for our coefficients. And then once you get these separated rational functions, you just integrate them using the rules we know. Now, something we want to keep in mind when we're doing a partial fraction decomposition is that we want our rational function to be what we consider a proper rational function, okay? So we're going to look at what makes something proper versus what makes something improper in terms of our rational functions. So what we want, like I said, is we want proper. So for something to be proper, we need the degree of the numerator to be less than the degree of the denominator, right? So what this means is that, in other words, I need the denominator's degree to be larger than the degree of the numerator, right? Similarly, if it's improper, which is this would be when the degree of the numerator is greater than or equal to the degree of the denominator, okay? So like I said, this is what we want. We want a proper rational function. And if we're given an improper rational function and we need to therefore make it proper, what we're going to do is we're going to do a polynomial long division. Okay, so if we are in a situation where our rational function is improper, which means the degree of the numerator is either greater than or equal to the degree of the denominator, we're going to go ahead and use a polynomial long division process to get our rational function into some proper rational function form. And then once we're here, we can go ahead and perform partial fraction decomposition. Okay, you do not want to start performing partial fraction decomposition if you're working with an improper rational function. Okay, you have to do the long division first, get it proper. Let's say our first example, I want to take 2x cubed minus 8x squared plus 1, and I want to divide that by x squared minus 4x. So here we're not even integrating just yet, okay? Let's just say we have this rational function. And what I'm going to do is I'm going to go ahead and just perform long division on it, because what I notice is that it is currently improper, right? So what we see is that the degree of the numerator, that's 3, is certainly greater than the degree of the denominator, which is 2 here, okay? Note that even if this was squared, right, or maybe we say we just cut this term out, right, altogether, and we get degree 2 here and degree 2 here, this is still improper, right? If you ever see an integral, or really any expression that we're going to be working with here, and these have the same power, I would recommend you do a long division, okay? It's going to make your problem way easier to work with, right? So let's go ahead and do our long division. So looking at this, our long division, our setup, looks a little bit like this, okay? So x squared minus 4x, and this is going to get divided by, we're going to put our numerator inside here. And what we're going to try and do is we're going to make sure you have a slot for every single term that would be in your polynomial, right? So look at this in descending order. This is x cubed, x squared. This would be for x, and this would be for the constants. You want to leave a placeholder here, okay? This is so that when we start to do the flow and we start to figure out the terms that would actually divide this out, you're going to want to make sure that everything has a place. You're not going to want some x cubes here, some x squareds here, and then if this was the 1, where are you going to put your x? Well, these don't align anymore, right? So you want to make sure you have space to align everything properly. It's going to make your flow a lot easier, okay? So let's go through this process, okay? So we are trying to do this division. So when we do long division, we think of, okay, what value, what thing could multiply by x squared to produce 2x cubed? Okay, well, what thing multiplies by x squared to give me 2x cubed? It's 2x, right? So 2x times x squared would be 2x cubed, okay? Now, this 2x, it doesn't only multiply to the x squared, it also multiplies to the negative 4x, right? So this is the whole expression you're trying to divide by. You're not just going to ignore this and only handle the x squared. So when you take 2x and you multiply by negative 4x, you also get negative 8x squared, right? Okay, so we have this. What you do is you subtract this line. So 2x cubed minus 2x cubed, those are going to cancel. Negative 8x squared minus negative 8x squared would be plus 8x squared. Those would cancel. And what you notice is that all of this goes to 0. They cancel. Okay? So once you kind of cancel out, even if it's just the first one or however many, you move to the things that are remaining and you drop those down. So in our case, we drop this 1, and then we try and go through the process again. Now, what number could you multiply, or what thing, not necessarily a number, right? What term could you multiply by x squared to get 1? Well, in this case, nothing, right? So we could obviously put some fraction form, but we're trying to keep things without these ugly fractions. So there's nothing that could multiply by x squared to get to 1, right? If this was x squared, then we could multiply by 1 to get x squared. But it's not x squared, right? It's just 1. So there's nothing that we're going to do left. What this means is that we perfectly divided this out into 2x with a remainder of 1. So the 2x divided perfectly, but I still had this 1 lingering. That 1 I was not able to divide by x squared minus 4x, right? So this means this whole rational function is equivalent to 2x plus 1 over x squared minus 4x. Now, hopefully you're noticing that is really ugly. I probably wouldn't have been able to integrate that. But if I was integrating instead just 2x, I could do that. And then the integral of 1 over x squared minus 4x, well, that would just turn to the partial fraction decomposition process we just talked about, right? I would turn this into 1 over x times x minus 4. I would then try and split this up into a over x plus b over x minus 4, and I would go through and solve the process for that. Okay? So hopefully this is making some sense, right? We're going to use our long division. We're going to tackle these improper rational functions. We're going to turn them into proper, and hopefully we get a nice integral in the end that we'll be able to work with. Okay? Now let's go ahead and try one more long division just to really solidify this here. Make sure we got some practice on this. Let's say I wanted to take x to the power 4 minus x squared plus 4x plus 2, and I'm trying to divide that by x squared minus 1. Okay. So again, notice that this is an improper rational function. So we notice the numerator has degree 4, the denominator has degree 2. Okay. So we're going to go ahead and try and tackle this. Let's set this up, same deal. Okay. So we got x squared minus 1. And we have x to the 4 minus x squared plus 4x plus 2. Again, notice how I left a space here, okay? x4, x3, x2, x1, constant. Now, what term would multiply by x squared to produce x to the 4? Well, x squared, right? X squared times x squared would give you x to the 4. X squared times negative 1 would also give you negative x squared. Go ahead and subtract this new row I created. We get x4 minus x4 cancels. Negative x squared minus plus x squared also cancels. That means I just drop my remaining terms, right? I drop the 4x plus 2. And the question becomes, what term could I have that multiplies with x squared? So what term multiplied by x squared would produce 4x? We don't have one, right? So we're not going to have anything that's going to multiply by x squared to produce 4x because this is now a smaller degree than this is, right? So we're stopped there, okay? So in this case, we're done. What that means is up top, our division produced x squared, which was able to get perfectly divided out. But then I was left with a remainder of 4x plus 2, which couldn't be divided by the x squared minus 1 successfully. Right? So this is now what we're working with. Well, again, think about the integral. If I was integrating this, pretty ugly. Right? But if I was integrating this, x squared super easy to do, power rule. And then this, a little bit trickier, but again, hopefully you notice that we could take this and just split up the denominator, right? So we could take 4x plus 2. This is divided by x plus 1, x minus 1. Then this could be split up using partial fractions, right? You take x plus 1, you take x minus 1, we put an a and a b, we follow our flow, right? Perfect. So that is our partial fraction decomposition. Now, when we do our partial fractions, we're going to have different types of factors that we're going to need to keep in mind. In all of the examples we discussed above, these have all been linear non-repeating factors. Okay, so what does that mean? Let's go down here. So linear non-repeating factors. Linear non-repeating factors come in the form of ax plus or minus b. And so what we see is that if you have some factor like this in the denominator, for example, if we look up above, this and this are both in that form, right? X plus 1, x minus 1. They both look like a linear function, a line. Y equals some mx plus b type form, okay? So it's basically degree 1, a linear term. And it's not repeating because you only see this factor once, right? There's only x plus 1 showing once in this denominator. So if you have this form, this is supposed to decompose into an a over ax plus or minus b when you do your partial fraction decomposition. Okay, so this is the flow we've seen, right? So you take some linear term, you throw up a constant on that, right? And then this would continue on if you had more factors, right? So you'd get another one with a b, a c, a d, and the flow would keep going for each of the factors you have, okay? So let's go ahead and try an example for our linear non-repeating factors. We've already done one just like this earlier, but let's go ahead and try one more just to really solidify our linear non-repeating process. So let's say we were asked to integrate x plus 14 over x squared plus 7x plus 10. So we want to compute this integral. Well, first things first, we're going to take a look, and of course we're in the partial fraction decomposition video. We're expecting to do partial fraction decomposition, but let's say we didn't initially think that we were supposed to do a partial fraction decomposition. Looking at the problem, hopefully you notice that a u sub is maybe possible, right? So if I let u be the denominator, just a quick write out, then the derivative du would be 2x plus 7 dx. Okay, well, the numerator doesn't quite look like that, right? Maybe you do a little bit of work, you try and break it apart. There's something there, we could definitely try it. But I do see that this is a rational function, right? Polynomial on top, polynomial on the bottom. I do also notice that it's proper. Degree of the numerator is 1, degree of the denominator is 2. So I also notice that the denominator is factorable, right? I can definitely factor x squared plus 7x plus 10. So all in all, I'm thinking maybe u sub is not my best bet. Maybe I'll just try and do a partial fraction decomposition. So what would I want to do with this? Well, I'm going to decompose this into, we're going to have to see what our factors become. What are the factors of x squared plus 7x plus 10? X plus 2, x plus 5, right? So like we talked about, we're going to go ahead and factor this. And then what we'll do is once we factored it, we're going to go ahead and make our split, right? We're going to decompose. So we take our x plus 2 and we take our x plus 5 and we throw on, because each of these are linear, right? They're power 1 and they don't repeat. You don't see multiple x plus 2s. There's no squared or cubed or something. You just put a constant coefficient, an a and a b. Now, we go ahead and produce that working equation that's going to help us to solve a and b. So what does this look like? Well, we can go through the whole process, but what I want us to notice is that if we do kind of a little tricky cross multiplication here, we will produce the numerator of the side with the coefficients, right? So in order to create a common denominator, because these are non-repeating, right? You would take a and you would multiply top and bottom by x plus 5. So what I can do is I can just ignore all of my denominator together and just figure out what the numerator would have been, okay? So hopefully everyone's seeing that, right? I can take the a, multiply it by the x plus 5, kind of like a cross multiplication almost. And then I'll do the same thing with b, right? I'll take the b and I'll multiply it by the x plus 2. That should give me the numerator terms. And then remember, if I'm ignoring the denominator, that'll be equal to just the numerator over here, okay? So that'll give me x plus 14 equals this, right? Remember, this is an aside. This is not part of the integral process. So this is not showing the same flow, right? So if this is true, if x plus 14 is equal to a times x plus 5 plus b times x plus 2, we're going to go ahead and solve a and b. I'm going to use the Heaviside cover-up method. Again, what we should have noticed by now is that this is a little bit quicker, especially for, like I said, the linear terms. So these are linear terms. So what I'm going to do is, with the Heaviside cover-up, strategically choose x values so that my coefficients cancel out. I'm going to strategically choose x to be -5 to make this go to 0. And then I'm going to strategically choose x to be -2 in order to cancel out the b term. So let's start with -5. -5 plus 14 would give me 9. Cancels this out. -5 plus 2 is -3b. This tells me that b would be -3 when you divide. Similarly, at x is -2, I lose this b term, right? This is gone. I get -2 plus 14, which is 12. -2 plus 5 is 3, 3a. A would be equal to 4. Okay? So what I notice is that a is 4, b is -3. I can go ahead and replace a and b in my decomposition, and then I can try and just tackle what each of these integrals are going to be. So starting back up with my integral, we see that we're integrating 4 over x plus 2. I'm just going to do a rewrite here. 4 over x plus 2 minus 3 over x plus 5. Again, with this, we should notice these two integrals are going to be natural log integrals, right? We use the memorization rule. Integral 1 over x becomes ln absolute value of x. Technically, we would want to do a u sub, right? U equals x plus 2. The derivative would be dx. Note how, since the derivative is just 1, it doesn't impact the process. You don't actually need to show the u sub here. Same thing over here. If you let u be x plus 5, the derivative is just 1 dx. Therefore, this is just a 1 over u, right? You would just do, or technically 3 over u, you get 3 ln u, and you plug in u. So there's not a huge mystery here. We're just going to go ahead and automatically apply our ln without doing this whole u sub process. And we should end up with 4 natural log absolute value x plus 2 minus 3 natural log absolute value x plus 5 plus c. Okay, again, plus c. Don't forget, we're doing an indefinite integral here. Now, linear non-repeating factors are not the only factors that we're going to see. We might also see linear repeating. So let's cover this. So if we have some linear repeating factors, this is going to, of course, fit a different form and therefore have a different decomposition. So these are going to have the form ax plus or minus b, same as our linear non-repeating, except now this is going to be raised to some power n, right? So if you have some linear term, remember the inside is still linear, it looks like a linear function, power or degree 1. It's just showing that linear factor multiple times by being raised to this power. This is going to decompose into still linear, so the constant up top, right, a constant coefficient a over ax plus or minus b. And then what we're going to do is we're going to add to it another constant coefficient b over ax plus or minus b squared. And what I'm going to do is I'm going to keep going, keep creating rational functions where the numerator is going to be this constant coefficient a, b, c, and so on. And the denominator is going to be the same factor, just increasing degree. So power, right? Power 1, power 2, power 3, and so on until you reach n, right? So until we reach this last term where it's ax plus or minus b to the power of n, and then this is whatever the constant coefficient we've gotten to is, right? Maybe if you have enough of them, you get to, let's say, f or g or h or whatever it might be, okay? Again, the numerator, the a, b, and so on, this constant coefficient is because it's linear, right? And then the denominator increasing power 1, 2, 3, and so on is because it's repeating, right? So those are the determining features here. The numerator, the constant coefficient, a, b, c, and so on is because they're linear terms. And then the increase in the power as you go across, that's because it's repeating. So with this, what we're going to do is we're going to try another example just to illustrate how this might break down. So let's go ahead and take a look at this integral. We're going to integrate 5x minus 2 over x plus 3 squared. Okay, 5x minus 2 over x plus 3 squared. Now, again, looking at this, maybe you want to try USA, maybe you want to try all these different techniques. What we should notice is that it is currently a rational function, polynomial on top, polynomial on bottom. It is proper, right? The degree of the denominator is 2, the degree of numerator is 1, and the denominator is factorable. It's already in a factored form, right? So all in all, kind of fit in all of the conditions that I would think would make perfect sense to do a partial fraction decomposition. I'm going to go ahead and set up my decomposition. So remember, x plus 3, it's a linear term, okay? It sure is squared, which means the factor shows twice, but that just makes the linear thing repeat 2 times. It doesn't make it a quadratic factor, okay? Very important. This is a linear, not a quadratic term. The 2 just means it's repeating. So if it's linear, it gets a constant coefficient, a, b, c, and so on. And because it's repeating, it's going to increase the power of the factor up to 2, because 2 is where we're being told to stop at. And then that's going to get a b as well. Okay, remember, it's a linear factor. Even with the squared term, that doesn't change the fact that you're putting the constant coefficients up top because these are linear factors, okay? So don't get tricked up on that. Just because this is squared doesn't mean that this now becomes the rule for quadratics. All right, so we got our A and our B. Let's set up our equation. Now, in this case, think about the working equation we're going to want. 5x minus 2, this numerator, is going to equal what? Well, if you were to get a common denominator here, hopefully what you notice is that this b term actually already has the denominator you want. It already has the x plus 3 squared. So when you solve to get a common denominator, you actually won't need to multiply b by anything. It's already got your denominator, right? But a doesn't have the x plus 3 squared. It only has x plus 3. So this first term, you would need to multiply by x plus 3 over x plus 3 to get the common denominator. But then the b wouldn't get touched. And so what you notice is that this should be the numerator on our right-hand side here. So that'll be the numerator of the fraction we get. And so I'll just clean this up. A times x plus 3 plus b. If it helps you, if that wasn't making too much sense, I would just go ahead and rewrite this whole thing on the side with the common denominator, and you'll see very clearly that this b term doesn't get anything multiplied, whereas the a gets the x plus 3. Now, once we're at this step, as usual, decide what method you want to use. Again, I'm going to just try and do the cover-up method. I'm going to decide x to be -3, right? I strategically chose -3 because I knew that would go to 0. If I get this plugged in, x -3, you get -15 minus 2, -17 equals b. Cool, look at that, I just found b. Now, from here, we take what? Well, what x value could you strategically choose to cancel out one of the coefficients and get the other? Here, there isn't a nice x value to plug in, similar to the other processes that we did, right? So the -3 was able to handle this term, but since this doesn't have an x in it, it doesn't have a perfect x value to plug in to nicely cancel. Okay, well, that doesn't mean that we can't use the cover-up method, right? So we just found what b is. So theoretically, we don't need to cancel it anymore, right? We don't need to cover it up. We just need to plug in some number that maybe makes the calculation nice to where I can get a with the b value plugged in. Okay, so for me, what I'm thinking is, and this could be anything, but I'm thinking I want to plug in x to be 0, just because this kind of made that side really big over here, and I'm trying to not have such large numbers. So I choose x to be 0. Left-hand side is -2. The right-hand side becomes 3a, and then b was, of course, -17. So we just plugged it in, right? Now we can still solve for a, right? There's only one unknown. We go ahead and find that 3a, if I add the 17 over, is equal to 15. Therefore, a would be 15 over 3, which is 5. Great. So now I've gone ahead and found my a and my b value. What I'll do is rewrite our integral with these constant coefficients plugged in. So 5 over x plus 3 minus 17 over x plus 3 squared. And now all I have to do is integrate. Well, again, ln rule, right? Technically, you could do the u sub, but it is going to be an ln. Now, in this case, this is not going to be an ln rule, but we're going to be able to do still the u sub. So imagine if I rewrote this -17 x plus 3 to be -2. You could just let u be x plus 3. du is dx, and therefore this turns into -17u to the -2. You certainly know how to integrate -17u to the -2. It's just a power rule. Okay, so again, first term, we get 5 ln absolute value x plus 3. If you do this whole u sub process, which again, this is not a huge mystery here. As you get better with u sub, you'll likely get better and better at identifying this without having to write the actual u sub process out. But what we notice is that if you were just to integrate right here, you get -17u to the -1 over -1, which is plus 17u to the -1, which is 17 divided by u, which is 17 divided by x plus 3. Okay. And then we throw in our plus c because, again, we're working with these indefinite integrals. This would be our solution there. So again, getting some practice with our u subs. Hopefully we're feeling good at kind of computing these a little bit quicker and just identifying that when the derivative doesn't have any extra terms like that, it's just a value 1, we can speed the calculation up. Okay, so what we've done so far is we've looked at the linear factors, both repeating and non-repeating, but we haven't looked at quadratic factors. So we're going to go ahead and look at quadratic factors. And in particular, we're looking at what we refer to as quadratic irreducible. What this means is essentially that this quadratic can't be broken down into linear factors, right? Because if it could, then you would just break it down and use the linear factor process, right? So this is a quadratic irreducible. And what we're going to do is we're going to do the non-repeating for right now, okay? So we're going to talk about quadratic irreducible non-repeating factors. And then we're going to go from there, right? So what does a quadratic irreducible non-repeating factor look like? Well, it would be of the form ax squared plus bx plus c. So just as you'd expect, a quadratic. Now in this case, this quadratic is going to have a, b, and c values to which it can't get broken down into two nice and easy linear factors, okay? So this cannot be broken down. And if you notice something of this form, this quadratic irreducible form, it's going to end up with the form of course, the denominator being that factor. So in our decomposition, we've always put the factor in the denominator. But the numerator is going to actually be ax plus b. So this is now not a constant coefficient up top. It's not just a single a or a b or a c. It's now a linear term, right? It's essentially almost like the y equals mx plus b, right? Ax plus b, cx plus d, and so on. So this is going to be our breakdown, right? The decomposition form for a quadratic irreducible non-repeating factor. So let's take a look at an example. We'll follow the same flow, see what our breakdown looks like, how we can find our coefficients, and then after that, we'll look at repeating quadratic irreducible factors. Okay. So our integral for this example is going to be negative 2x plus 4 over x squared plus 1 times x minus 1. Note here that you have a quadratic irreducible, so this can't be factored, right? X squared plus 1. And you have x minus 1, which is just a linear term. So you've got a little combo of a quadratic irreducible and a linear factor here. Note none of these are repeating, right? There's no squared, no cube, nothing like that. So in order to break this down, since it's already in a factored form, I just go ahead and create my denominators. So x squared plus 1, x minus 1. And what I'm going to notice is that the first term is a quadratic irreducible, which means it's going to get ax plus b, kind of this linear term up top. And then since this is a linear denominator, linear factor, it's going to get a constant coefficient up top, so a c. Hopefully that is making sense. So this fits our form with the quadratic. This is a linear, so you get a single constant there. Now our goal is what is a, b, and c, right? We have to go ahead and find what these are going to be. Well, let's do this. Let's say get our working equation as always. So you're going to take negative 2x plus 4, which is the numerator on this side. And if I were to create a common denominator over here so that we could cancel out the denominators and only compare the numerators, the right-hand side would look like ax plus b times x minus 1. So this would need to get multiplied by the x minus 1 to get the common denominator, right? Again, that kind of almost cross multiplication-esque process. And then the c value, it needs to get multiplied by the x squared plus 1 because there is no x squared plus 1 in the denominator currently. With this being said, we have this ugly working equation now. And at this step, what I see is that I need to decide if I want to do the Heaviside cover-up method or if I want to do the polynomial mirroring. Generally, when I'm working with quadratics, I'm inclined to do the polynomial mirroring, but that doesn't mean that the cover-up method won't work, okay? And so what I'm going to do here is I'm going to again do the cover-up method, okay? So first things first, what am I going to strategically choose? Well, right away I see x equals 1 would be a great choice because x equals 1 would actually cancel out a and b, and I would be left with just c. So here's what I'm going to do. I'm going to say x is 1. And if x is 1, I get negative 2 plus 4, which is 2 on the left-hand side. On the right-hand side, I said that's gone. I get 1 squared plus 1 is 2, 2 times c. So 2c, c is 1. Cool, okay. So just with the cover-up method, I've already found one of the 3 coefficients that I need really quickly. Now I go again and I think, okay, well, what else could I do? Could I choose any other x values? Well, here, obviously I can't choose anything to get rid of this term, right? Because there are no real values that we can plug into this to make this term go to 0. I could plug in x to be 0. Right, so note right here, if I plug in x to be 0, I can actually get rid of the a term, which means I can solve for b. And since I already know what c is, there's only one unknown. B is the unknown. So this actually works somewhat nicely. X being 0, I get left-hand side is 4. Right-hand side would be, obviously this is gone. You get b times 0 minus 1, so negative b. And then c being 1, when you plug in 0, 0 plus 1 is also 1, so you get plus 1 over here. That tells me then that b would equal negative 3. And then now the question is, what other x value could you choose in order to now find a? Well, again, similar to the one we did previously, you just choose a random one. Right? So there's no other good, quote unquote, good ones to choose, right? but you could just choose any x value. And ideally, you're going to choose an x value that makes your calculations a little bit easier. So for me, when I'm looking at this, I'm inclined to choose some small numbers for x, right? Notice how here 0 and 1 I'm already choosing. I might choose x to be -2, or I might choose x to be 2, or I might choose x to be -1. Numbers that are relatively small, that way this calculation doesn't go crazy. What I'll do is just choose 2 here. Okay, I'll do +2. And that's just kind of me looking at this left side and to know if I choose +2, then I'll actually go to 0. This works somewhat nicely. So let's choose +2. I get 0 on the left-hand side. On the right-hand side, I get 2a -3. Right? So a times 2, 2a, b was -3. And then that's also multiplied by 2 minus 1, which is just 1. So I can just leave 2a minus 3. And then c was 1 times 2 squared, 4 plus 1 is 5. So that's plus 5 times c, which is 1. So 5 times 1 is 5. Cool. That means 2a is now equal to, this simplifies to 2. When I move it over, I get -2. A would be -1. So now I've got all my coefficients. Go ahead up top, plug in. So we get the integral, -x minus 3 over x squared plus 1 plus 1 over x minus 1. All right, what do we notice? Well, I noticed that the second term here, the second rational function, is a natural log rule, typical integral we've been seeing this whole time. This is a little bit trickier, right? This first term here, a little bit trickier. As of right now, if you attempted to do u sub, so let u be the denominator, its derivative is 2x. That would only be able to handle essentially this term, right? The term with x. It doesn't handle this constant. And so what that means is I actually need to go ahead and take this integral and I need to split it up, okay? And this is a common practice. You want to be comfortable being able to split up your integral. Just remember that you can only split up from the numerator. What I mean by that is here I can do -x over the entire denominator and then I can do -3 over the entire denominator. You wouldn't be able to take your x squared and split it with the terms on top and then the 1 and split it with the terms up top. That's not allowed, right? You could only split from the numerator. And so what this would look like is I would get integral -x over x squared plus 1 minus 3 over x squared plus 1 plus 1 over x minus 1. And now we're going to use our integration skills and we're going to tackle this here. So this first term, like we said, is going to be u sub. So this is a u sub. This right here, hopefully you can identify it. Take a second here really quickly. What is it going to be? It should be an arctan memorization rule, right? 1 over 1 plus x squared. And then over here, this is just going to be an ln rule, right? Technically a u sub, but it's a simple one, so we're just going to call it an ln rule. And so what do you get if we do all this? Well, for one of them, I'm going to write the u sub just so we can make some sense of this. So remember, if you choose u sub here, u would be the denominator. The du, like we talked about, would be 2x dx. Since you don't have 2x, you just have an x. That would mean that x dx is du over 2. So I should have a 1/2 of my problem. Again, if you're good with u sub, you might have already seen this. So what this means is that when you integrate this, you're going to get -1/2 integral 1 over u du. So all I did was I pulled out the negative, I pulled out the 2 that would have gotten put in, and then the bottom became u, right? Now, the rest of it becomes 3 arctan x, or 3 tan inverse, right? However you want to write that notation. And then over here, this becomes ln x minus 1. So I'm just doing these other ones for now, just so that I have them. The u sub, what does this become? Well, when you do the u, it becomes -1/2 natural log of u. These we can make copies of again. And then all you're going to do is, as usual, replace our u. So our u was x squared plus 1. This, make that look like a 2. This would be our final answer for this. And again, note, that with our ln's, we could be combining these, so I don't spend a lot of time worrying about the rewrite, but since these are both ln's, you could use some log properties and combine these together. Not a huge deal if we don't do that. I would just leave it like this. So that's what we got, right? And the only thing we didn't look at, and what I'll quickly mention here, is let's do a quadratic irreducible repeating. So what happens when we have a repeating quadratic irreducible? Now, I'm just going to put the form here. I'm not going to do an example just because this, as you can imagine, is going to be quite a pain, but it's just going to be the form ax squared plus bx plus c to some power of n. And if you do have this, what would the decomposition form come out to be? Well, it would be ax plus b over ax squared plus bx plus c. So this is using our knowledge that we learned from the linear and the quadratics, right? We're combining everything we know. So you get single quadratic on the bottom, right? Single power. And you get the ax plus b up top because it's quadratic. And then because it's repeating, you'd get the same factor to the power 2. And then blah, 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 3, 4, 5, and so on, right? So this would just keep going all the way up to n. And then your next numerator would be cx plus d, and then it would be ex plus f. And whatever the numbers that you need to get, you just keep going, right? Add more constants and so on, making sure obviously you change these, right? You don't want to use c somewhere, and then if you have a linear term, also use c. Everything has to be unique, right? Okay, now I know I said I wasn't going to do an example, but I am going to do an example. This time, I'm just not going to solve for the coefficients. Okay, we're just going to show basically the decomposition, leaving the coefficients as the placeholders. All right. So in this example, let's say we're given integral of x squared minus 2 over x squared plus 6 cubed. All right. So looking at this, again, it is a rational function. It is proper, right? The degree of the denominator is actually 6 here. Numerator is 2. That works out well. The denominator is also factored, right? It's in a factored form. In this case, the x squared plus 6, this is a quadratic, of course, right? Squared. And it is irreducible because we cannot go ahead and break this down into any linear terms. Right? So you think about the solutions of this. If you were to just solve x squared plus 6 equals to 0, you would get x equals square root, plus or minus square root of negative 6, which of course, those are not real numbers. So for us, we're talking about the real values here. And so this is irreducible and it is repeating, power 3. Okay. So applying the logic we just set up here, this would simply break down as ax plus b over x squared plus 6. So it's a quadratic. It gets the linear numerator ax plus b. And because it's repeating, I'm going to just put the factor to power 1 for now. And then I'm going to increase the power to 2 and then to 3. And we'll go ahead and put our numerators on this as well. So you see, again, repeating up to 3. So 1, 2, 3. And our numerators, since these are all quadratic terms, right? They're all x squared plus 6, x squared plus 6, x squared plus 6. I would get a cx plus d and an ex plus f. As you can imagine, the reason I'm not solving for this is because now I have 6 unknowns. I would have to do a little bit of legwork to find all of these. And for the sake of time, we won't do that. Hopefully with this example, you have an understanding of how we would approach a problem if it did have these quadratic irreducible repeating factors. If you're looking for a little bit more help on this, you can check out my website, which has the notes, as well as some practice problems that you can take a peek at and work through. Make sure you master this topic.